Next, we come to ideal gas. Remember, I said we want to study gases because gases are good for doing work. We can easily compress them and then let them expand. And in the process, we can recover some heat, some energy, use that energy to do work. Yeah? Like you might have heard of steam trains. These were some of the first things that we used in the Industrial Revolution. Okay? So we're going to study an ideal gas, not a particular gas like oxygen, nitrogen, and so on. We're going to idealize it so that we're going to say that the molecule, whatever it is, we're just going to represent it by a point particle. Okay? So let's read this first. An ideal gas is a theoretical gas. Okay, so it's not a real gas. Composed of a set of randomly moving, non-interacting point particles. So we have each molecule, let's say of nitrogen or something, which is just a dot and it's randomly moving depending on the temperature. Yeah? So its velocity depends on the temperature, but it moves in all directions randomly. The ideal gas concept is useful because it obeys the ideal gas law, which we'll come to later what that law is. And it's a simplified version of the equation of state. What's an equation of state? An equation of state is a relationship between the temperature, pressure, volume, and amount of a gas. Okay? That amount is moles typically. So we'll first learn something about that. So equation of state relates pressure of the gas. We know pressure is in pascals. Sometimes it's given in atmosphere. Pascal is same as Newton per meter squared. Now, volume, we're going to measure in meter cubed in SI units. It could be given in centimeter cubed, liters, milliliters. You need to be able to convert from all of them to meter cubed. Amount of gas will be in moles. Okay, we'll define moles a little bit later on. It's just a number, so it has no dimension, no units. Temperature of the gas is always going to be in Kelvin. Remember, that's our temperature in SI units. So the pressure, volume, and temperature and amount of gas are related together by the equation of state, and a simple version of equation of state is the ideal gas law. So we'll see that simplified equation of state a little later on in this section. So consider a gas that is placed in a container. Now, whatever amount of gas I put in, however many molecules, it's going to expand to fill the entire volume of the container since it has no fixed volume. We learned that in the states of matter, right? Its temperature for the gas is a measure of its internal energy. Okay, let me explain this. So internal energy, I said all the energy of your system. Your system is just this gas. We define that in this gas, there's no interaction between particles. So each particle is moving on its own. It is not held together with any bonds, anything. So there's no potential energy then in the ideal gas. There's only kinetic energy, energy due to motion. So it depends on the average velocity of the particles. Yeah, we call that VRMS. RMS stands for root mean squared. Some kind of average velocity of the particles is related to the temperature. Yeah, so kinetic energy, half mv squared. The mass is fixed. Yeah, but v, the velocity, is not fixed. So how fast it moves varies with temperature. The higher the temperature, the faster it moves. So temperature becomes a direct measure. Yeah? Its pressure will depend on several things. So pressure, first you need to understand what causes pressure. So imagine your container, let's say it's a cubic box, okay? And inside which you have, let's say, 50 particles, which are all moving randomly. Now these particles collide with each other. They have perfectly elastic collisions. We're going to assume that. They also collide with the walls and they bounce back again with perfectly elastic collisions. That bouncing, that change in momentum creates a force, which per unit area is the pressure. Yeah? So the pressure on the walls is generated by these particles coming and hitting the wall and bouncing off it. So clearly it depends on the size of the container then, or the volume. If I make my container bigger and keep the number of particles the same, then I'm going to have fewer collisions on the side because now it takes longer for my particles to find a wall to collide against. So it's inversely proportional. The bigger the volume, the smaller the pressure. It also depends on the temperature, because these particles, how fast they are moving, will determine how much change in momentum we have upon collision with the wall. And that velocity, we know, is determined by the temperature. The higher the temperature, the greater the change in momentum, the greater the force, therefore the greater the pressure. So we expect a direct correlation. Higher temperature, higher pressure. It also depends on the amount of gas. If instead of 50 particles, I now had 100, I double them, then clearly I'm going to have more collisions on the wall, yeah? Keeping other factors the same. So keeping the volume at the original volume and the same temperature. At one time, you vary only one factor, and you look at its effect. So if I double the amount of gas, I'm going to get much greater pressure, double the amount of pressure. So again, direct variation between N and P. Okay, so pressure, volume, and temperature and amount of gas are related together by the equation of state. Typically, this can be quite a complicated equation. Okay. We will study the simple version of that equation, which is the ideal gas law. So what have we said? The characteristics of an ideal gas are that we have atoms or molecules that move randomly. There are no long-range forces between one particle and the other. Each particle is individually like a point occupying negligible volume. And these conditions are actually not too bad to apply to a real gas at standard temperature and pressure. We call that STP. So what is standard temperature and pressure? Standard temperature is like 0 degrees Celsius. Okay, so freezing point of water. And standard pressure is 1 atmosphere. Remember, we're all under 1 atmosphere pressure all the time. Okay. When you go to other temperatures and pressures, this approximation, the ideal gas approximation, applies well, provided your temperature is high. So at higher temperature, your particles are further apart, which is more like an ideal gas. Yeah? And low pressure. Okay. At low pressure, also your particles are further apart. Okay. So under these conditions, you can easily idealize your gas and use the ideal gas law to study a real gas.